Okay, my notation wasn't actually that bad, but I corrected a couple of smudges up here. So we've got a parameterization of a spiral. Here's the parameterization by this function where theta goes from theta 1 to theta 2. Here's our partition of the interval from theta 1 to theta 2. We take our typical subinterval, our ith subinterval, and our f sub I is actually, I said f sub I of r of theta sub I star, and my r should really be the r vector, so that now f sub I star will be a vector that depends on the angle theta, because of course the angle theta determines the direction of the force vector. Well, turns out that's very easy to do. You got g of m1, m2 over your magnitude of r of theta sub I star squared. Now your r of theta sub I star is just how far you are. And that goes into the force function, as so. And then it's times your r vector at theta sub I. That r vector will be in the direction of the theta sub I, but it'll have a magnitude that depends on this path, okay? And over the magnitude then of r of theta sub I, and it should be theta sub I star in both cases. Well, your delta S sub I, as you can see if you think about this, let's just take a typical delta S sub I. Now that's going to correspond to a delta theta sub I. So it's going to be the change in position from one theta to the next. As calculated based on your delta S, on your theta sub I star, your sample point. If it's not a very straight line, but it's actually, you know, this, okay, it actually is intended to be kind of a curve because it does curve a little bit. But this slight curve you have on your delta S sub I, the path from here to here, is approximately a straight line, and it's at the hypotenuse of a right triangle, okay? The leg in this direction is just your delta R sub I, which is just your dr d theta times delta theta. Okay, just again a differential, the rate at which r changes with respect to theta by the delta theta that you have for that interval. Now that should be an I for the delta theta. And a couple of other little finer points I don't want to worry about. This leg is what? Well, it's whatever your radius at your sample point is, and I'll just call that r sub I, your distance from the center, multiplied by delta theta. And we've seen that when we did polar coordinates. That's just the arc length along something that's a good approximation of a circle, where you know the radius and the angle, okay? That is just definition of a radian. Meaning then that your delta S sub I, I'm going to put it into this figure here. Here's your delta S sub I. So your delta S sub I is the square root of this leg squared plus this leg squared. That should have an I in that delta theta. Okay? Which we can write as the square root of r prime squared delta theta I squared plus r squared delta theta sub I squared. Being a little careless with subscripts, it should be at least very plausible then that what we end up integrating is this, which is just, we factor out the delta theta sub I squared and take its square root. We're going to have our Ri prime squared plus our Ri squared times our delta theta sub I. Then, well, that's the magnitude of our delta S sub I, isn't it? Okay, that's of interest, but that's not exactly what we want, is it? So I'm going to try to insert that. I'm probably going to get rid of this because we already talked about it, and talk a little more extensively about what we do when we're doing a dot product, because that's what we actually have to do here.